SwayamPrabha. Digital India. Educated India.
Hello everyone. In this lecture, we'll be looking at problems on forced wetting and coating flows. Let me first explain why do I call it forced wetting as opposed to just wetting. Now, if I were to drop some water onto a surface, then natural processes such as gravity would basically lead to surface getting wet, right? So those processes are what we would call as just wetting. But forced wetting is a process where the user would actively cause the wetting process. Okay, one of the common examples where we would see forced wetting is this example of a painter using a paintbrush. Now, in this process, what the painter would do is to take this paintbrush and dip it into a bath of paint, and then when you pull it out, paint gets coated onto this brush. Paint gets deposited onto the brush, which is eventually transferred onto a wall. Now, there are interesting scientific questions that one can ask in this problem, such as how much of paint gets deposited onto the paintbrush, right? This could be relevant in many industrial problems where coating, the efficiency of coating is very vital. One such problem is the so-called roll coating process. And this is how we would make adhesive tapes. What you're seeing in this example is one such roll coating process. It's called the forward roll coating, where there is a pickup roller which is picking up adhesive or any liquid in this case, and then it's eventually getting deposited onto a substrate. The substrate in this case, I'm highlighting it in red. This is the substrate. This is a fast coating process. Another process is what is called as the dip coating process. In dip coating, as the name suggests, you dip the substrate into a reservoir of liquid, and then you would pull it up at a constant speed, and then in this process, you would basically get a coating onto the substrate. Now, the dip coating process specifically is shown schematically here. Now, what you're seeing in the schematic is the process of dip coating shown in two dimensions. The substrate is moving up with a velocity u, and there is an interface which is separating two fluids. In general, we are only interested in the role of air above is not very vital, and it can be ignored, right? So the question that we are interested in asking is, what is the thickness of this coating? We'll call it as H infinity as a function of liquid parameters. What are the liquid parameters? The viscosity of the liquid, density of the liquid, and then we have some flow parameters such as velocity of the plate, right? We have gravity, and finally we have surface tension, right? So surface tension acts as the interface between the liquid and the gas above. So you can imagine that the plate, when it's going up, because of viscous drag, it is pulling the fluid up and trying to create a coating, whereas gravity is pulling the fluid down, and surface tension, because of the enormous increase in surface area, you would expect surface tension also to oppose this phenomenon. So now there is a nice balance between these forces: viscous drag, which is pulling it up, and gravity and surface tension opposing it. So when you have a situation where multiple forces are competing against each other, it is possible that you can have a steady state flow condition. A steady state flow condition is where the geometry doesn't change with time, and we can analyze it as a time independent problem. Now, how would we go about studying this problem? I'm showing you two schematics. In the left panel that you see here, there is a substrate which is dipped into a reservoir, but the substrate is not moving. So this you would call as a static meniscus, right? In a static meniscus, there is a balance between surface tension, force, and gravity downwards. And this results in a length scale LC, which you have already seen. This is called the capillary length, and the capillary length would be surface tension divided by the density difference, delta rho, times gravity. Okay, right? And for air water, we know that the capillary length is approximately 2.7 millimeters. We'll come back to this number later. Now, when you look at the coating problem, the same substrate is now being given a velocity u, right? And we want to determine the thickness of this coating. Let's go back to the jump conditions that we derived. The first step in doing this is to write down the normal vector, and we will call the fluid above as plus and the fluid below is minus, right? And we are only interested in the effect of the liquid below the interface. So we'll assume that the air above is passive. So therefore I have a liquid whose viscosity is mu and density is rho. So if I write down on what does the thickness of this coating H infinity depend on, the thickness of the coating would be a function of, as I already said, velocity of the substrate, viscosity, density, gamma, surface tension, and gravity, right? These are the parameters. Now we can use Buckingham Pi theorem and find that there are three non-dimensional numbers which govern this problem. Or in other words, we can show that the non-dimensional thickness, that is the thickness of the coating relative to the capillary length, is going to be a function of Reynolds number and capillary number, right? So here Reynolds number is rho u LC by mu. This is inertia to viscous forces. And then we have capillary number mu u by gamma. Okay. So this Reynolds number is inertia to viscous forces, and capillary number is viscous to surface tension. Note that if you think in terms of forces, there are three forces at play: inertia, viscous, and surface tension. And there's another force which is gravity, and gravity appears on the left hand side, and then Reynolds, inertia, viscous force, and surface tension will appear on the right hand side. This is the way we can think about it. Okay, but though one has to be careful because the Reynolds number is dependent on a length scale which inherently involves gravity, right? Now there are four forces. So now we have H infinity by LC, which is the thickness of the coating relative to the capillary length, depends on Reynolds number and capillary number. Now there's another way to think about why we should get three non-dimensional numbers. There are four forces. They are gravity, surface tension, viscous forces, and inertia, and therefore you should expect three non-dimensional combinations, right? So the RE here, this is ratio of inertia to viscous forces, and this is rho u LC by mu, and capillary number is the ratio of viscous to surface tension. Which is mu u by gamma, right? So for simplicity, we will restrict attention to low Reynolds number cases. So these are the cases where inertia is negligible. And this implies that Re is much smaller than 1. Okay. So in the absence of inertia, we have one force is being dropped out, and therefore the above relationship that I wrote between the thickness of the relative thickness of the coating versus Reynolds and capillary now simplifies to H by LC is some function of capillary number, right? And our goal in this lecture is to determine what is this relationship, right? So let's start with Navier-Stokes equations with boundary conditions. So we'll write down, this is only for the liquid that is being coated. So density times d by dt of u bar is minus grad p, viscous term, and gravity. L dot u bar is 0, right? And the normal stress balance that we know, we can write, I'll directly separate the normal stress balance into pressure terms and the deviatoric stress terms. We have P plus P minus the deviatoric normal stress plus minus Z dot n. Okay. We will assume that gamma is constant. Gamma is indeed constant in this, right? And if you were to write down the same thing for the tangential stress, because gamma is constant, the tangential stress is continuous across the interface. Now we can make further simplifications. Now remember, the plus is basically the fluid above, and I already said the gas is passive. Meaning its viscosity can be neglected. So mu gas is 0, P gas is constant, and you can just call it as some constant atmospheric pressure, right? So we can make some simplifications. So for example, the pressure above this can be thought of as a P atmospheric, constant atmospheric pressure. This term would be 0 because there is no viscosity, so the normal stress, this term doesn't appear, the deviatoric stress doesn't appear. The same is true for the tangent stresses as well, right? So we can simplify these equations a little bit. And now let's do one more thing. Let's non-dimensionalize these equations. So we'll say plate velocity is u. Okay, so implies I will say the non-dimensional velocity u would be u by capital U. Maybe we'll put a u naught to distinguish between the plate velocity and the fluid velocity, right? And we will non-dimensionize the length by the capillary length. Now we have choices for non-dimensionalization of pressure. We've already seen this in the past. The non-dimensionalization for pressure, this would be a viscous dominated flow. Therefore, in anticipation that Reynolds number is going to be very small, the natural choice of the length pressure scale would be the viscous pressure scale. Okay. We will also say that the pressure above, we'll call it as P infinity, right? So if I take these non-dimensional scales, and the time scale would be, if I substitute these non-dimensional scales into the problem, then we would have the total derivative, this would simply become u0 square by LC the pressure term would become as follows: mu u naught by LC square, viscous term. I'm first writing down the individual terms and then we will put everything together. So if we put everything together, what do we have here? Right? And I can divide throughout by mu u naught by LC square. We get a simple elegant non-dimensional form of these equations, and they would be Reynolds number times the inertial terms the pressure gradient term and finally we get 1 by capillary for the gravity term, right? Now we can multiply throughout by capillary number. What do we now have is Reynolds times capillary inertial term the viscous term, and finally we have 1. This is the non-dimensional form of this equation. Now if Reynolds number is much smaller than 1, then the equation simply simplifies to we have capillary number is equal to 0. Okay. One can also verify verify that the continuity equation del dot u is equal to 0 simply becomes del star dot u star is equal to 0. Right? Now we look at the normal stress balance. The normal stress balance would be minus mu naught by LC. I'll call it as P star plus mu u naught by LC. I've used the same non-dimensionalization for the deviatoric stress. And hat. Right? Now it's important to note here that I've made some small simplification here. The pressure P here P star represents the change in the non-dimensional pressure relative to atmospheric pressure. Note that if I have to write it down systematically, I would have a P infinity above, a non-dimensional version of P infinity. Either you can redefine P star as P minus P infinity, or without any loss of generality, you can also set P infinity to 0. Okay. If I were to continue this analysis, what do I have now is, if I divide throughout by capillary number, capillary surface tension, and cancel the capillary length, I have capillary number times P star, capillary number times tau nn, del star n. Okay, this quantity here is non-dimensional curvature. Okay, so this is how we would go about analyzing these equations. So now what we have is, we have all the three equations are shown here. The first equation is a balance between the pressure, viscous, and gravity. Then we have the continuity equation, which is for mass balance. And then finally we have the normal stress balance. Okay. Now, these equations, even though they are linear in velocity, there is a nonlinearity coming from the curvature. Further, solving this system of equations for the entire shape of the interface is not possible. There is no exact solutions. Okay. So we will follow the approach that Landau and Levitt and subsequently several authors have done. So the idea behind this process is as follows. Here's a substrate moving with a velocity u, right? And the interface that is of interest to us, this is the interface. Now you can think of dividing this interface into a few small parts or different regions. So let's first look at the region where the dashed orange curve is what you can call as the static meniscus. Why is it a static meniscus? Now, if you were to do this problem, and this is where the method of matched asymptotic expansions becomes useful. Now the thickness of the coating is so small in realistic applications that if you were to see this problem of coating from a region, from a length scale much bigger than the capillary length, then the coating would appear like this. So this would appear practically static, and this is the thickness of the coating. The coating is so thin compared to the typical outer region or the static region that for all practical purposes the coating appears to be at zero thickness, but we know that's not the case. We want to determine the thickness of the coating. So we divide this problem into several regions. Okay, the first thing is we will consider a region over here which you can think of as the viscous dominated region. Okay, in this region what you have is you have a uniform thin film. The flow is fully developed. And you have a region far away from the interface, where far away from the plate, this is a static region, and in this region gravity balances surface tension. So now we have two completely different well separated regions. So you have a very thin film, though my drawing is showing a highly exaggerated thin film. So you have a viscous dominated region where viscosity is the primary force, and then you have a static region where eventually you are so far away from the plate that the motion of the plate, the viscous drag from the plate, is not really felt, and you have to have balance of the other two forces, which is gravity and surface tension. This automatically means that there is a transition region where viscous stresses balance surface tension. So this is where we would actually think of as a problem as a matched asymptotic problem, where you actually have different regions. You have to get solutions in different regions and match the solutions from these different regions, right? Now, doing a full-fledged mass asymptotic procedure is beyond the scope of this course, but instead what we will do is to use clever scaling analysis to basically get the dominant scaling law. Okay, remember the scaling law that is of interest to us. So we will use scaling analysis to determine this relationship. Therefore, I will be sacrificing rigor and focus on the key elements of this analysis, and then for students who are keen on understanding this Landau-Levitch flow systematically, there are several excellent sources such as Gary Leal's book, which describes this problem, and one can actually look at other sources in matched asymptotic expansions where this problem is derived in detail. Now, How do we go about doing this analysis? Now let's divide the problem into two parts. So here's my plate again. Let's first consider a static meniscus, a static region. Okay. And then on top of the static meniscus, I now have a dynamic meniscus. Okay. So the dynamic meniscus is L here. Okay. And the plate is U. Okay. So dynamic meniscus is like the static meniscus, but now dynamic meniscus is also affected by the shape of the meniscus, also affected by viscous forces. Therefore, we call it the dynamic meniscus. But far away, the static meniscus and the dynamic meniscus would match, and you obtain the static meniscus. Okay. So in the static meniscus region, the fluid is largely unaffected by what is happening near the plate. Okay. Now further, in the dynamic meniscus region, the thickness, we call it as H. Okay. So let's also define a coordinate system more precisely. I will define a coordinate system which is y going this way, that is perpendicular to the plate, and x along the plate. Okay. So what do I now have is, we have the thickness which is a function of x. Okay. So if I were to magnify the dynamic meniscus, I have a dynamic meniscus here. The thickness of the dynamic meniscus, we call it as h of x. Okay. Now if you recall, the dynamic meniscus is nicely fits into this transition region. Okay, because transition region is where viscous stresses start to become important. Okay, so viscous forces dynamic region, you can approximately say this viscous force would be viscosity mu u by h square. Okay, recall that this term is coming in when if you look at this equation, the dynamic meniscus region, we have, this is a thin film which is basically, the meniscus is vertically steep, and you have variation. It's a thin film, so the variation along the plate is much smaller than the variation normal to the plate. Okay, so that's the first observation. Okay, so then in this region, the viscous forces are as follows. Now we look at the curvature force, surface tension, curvature force in this case would be, how would we go about deriving the curvature force? You have pressure gradient, so the viscous forces and now we want to determine the surface tension curvature force. Okay, now the surface tension or curvature force comes from pressure gradient, where pressure itself, remember, this is pressure if you look at the dimensional form of the Navier-Stokes equations, it will be surface tension times curvature, right? And this would be 1 by L. That's the variation along the meniscus as you go up, del P by del X. And this term would be gamma by LC. That's the typical length scale for the curvature. So the curvature is still dominated by the static meniscus curvature. And so if I were to balance in this transition region, if I balance these two forces, I have mu u by h square will balance gamma by L times LC. This is the first relationship. We'll call it as equation 1. Okay. Now in this relationship, both H and L are unknowns, right? So it means that we need another relationship to determine H in terms of other parameters. Okay. If dH by dx is very small, remember dH by dx is basically the variation of height in this dynamic meniscus. Okay. Then we can employ the lubrication approximation. Okay, and in this lubrication approximation, we have the curvature in the dynamic meniscus would be d square h by dx square. Remember the nonlinear term in the curvature, which is 1 plus dh by dx whole square whole to the power of 3 by 2. That term is negligible. The order of magnitude of this term is h by L square. Okay. Similarly, curvature of the static meniscus which you can call as kappa static goes like 1 by LC. Now, if I want the transition region here to smoothly match the static region, this will happen when the curvatures of these two interfaces in these regions match, so that we have a smooth transition from static meniscus as I approach the transition region. And therefore, for a smooth transition from static to dynamic meniscus, we require the curvatures on the static region to match the curvature in the transition region. The dynamic meniscus curvature is to match, and therefore I have h by L square should match with 1 by LC. This is my second relation. So now I have two relations here. Mu u by h square goes like gamma by L times LC, and the second relation is h by L square goes like 1 by LC. Okay. So eliminating L from 1 and 2, we get, so let's say I can take the second equation, L square goes like h times LC, and I can substitute this L in equation 1. What do I have now here? Mu u by h square goes like gamma by L, that is h power half, LC per half by LC. And this gives me the relationship H by LC per 3 by 2 goes like mu U by gamma. You can recognize that this is the capillary number, and we get the well-known classical result H by LC goes like capillary power 2 by 3. Now, if we carry out a systematic theoretical derivation following the so-called method of matched asymptotic expansions, we get the result that was originally obtained by Landau and Levitch. H by LC is equal to 9.9458 capillary power 2 by 3. This result is an unbelievably beautiful result because it involves all the parameters that we have considered, which is the capillary length has gravity and surface tension and density. Capillary number has viscosity, velocity, and surface tension. And the thickness of the coating, this gives me the thickness of the coating precisely, is been verified with many experiments. So this is also called the Landau-Levitch law. This gives me the thickness of the coating. Now let's confirm that the assumption that we have made is indeed okay. We had made the lubrication approximation, so let's check what is the length of the dynamic meniscus. Length of the dynamic meniscus L goes like H power half LC power half, and this, if you substitute the expression for H, you get LC to the capillary 1 by 3. Therefore, if capillary number is very small, L is very small compared to LC. Okay, so this is within the approximation that we have made of the dynamic meniscus. Okay, and strictly speaking, we need capillary to the 1 by 3 to be small. Okay, now we can make some estimates as well. Now, if LC is 2.7 millimeters, capillary number is 10 power minus 3, then we get H by LC goes like capillary power 2 by 3, which is nothing but 10 power minus 3 power 2 by 3, implies H by LC is 10 power minus 2, and therefore H will be LC, which is 2.7 mm by 100. Okay, this is 27 micrometers. So this is what I was referring to earlier as the static meniscus. If you see the panel on the right, the coating thickness is so small that the static meniscus appears very large compared to the thickness of the coating. So in other words, there is a scale separation in this problem. The thickness is so small that it's an inner region. In the language of mass asymptotics, you would refer to the coating as an inner region, and the outer region would be the static meniscus. Okay. This is the classic result of the Landau-Levitch law. There is another important result that also needs to be looked at, which is the so-called Landau-Levitch equation. So the question is, how do you get 0.9458? It's an order 1 number, it's very close to 1, but how do we still get it? So one has to numerically solve what is called the Landau-Levitch equation, which will be the subject of the next lecture. So thank you.